Okay, Linus Pauling's valence bond theory attempts to explain the formation of covalent bonds. So, very simply, we'll draw on your knowledge from orbital shapes and quantum theory to draw diagrams of the formation of these covalent bonds. And the primary concept here is that these covalent bonds form by the overlap of half-filled atomic orbitals. So we'll take something you're familiar with, an energy level diagram for hydrogen, and draw that right here. So for an energy level diagram of hydrogen, we know we have the 1s sublevel in which there's one orbital, and with hydrogen having just one electron, we can place one electron there. And so that's for hydrogen. Now, in the molecule H2, we actually have two hydrogen atoms. So to draw a valence bond theory diagram, I need to indicate the element with the element symbol in place of the nucleus, and then draw the orbital that is half filled. And so you see in the hydrogen that 1s orbital is half filled. And so when I draw an s orbital, I draw it spherical in shape. That wasn't very good, which really looks more like a circle at this point, but again, it's in 3 dimensions, and I can label that a 1s orbital. Now, in the H2 molecule, there's a second hydrogen atom, so it's going to look identical. It's going to have another 1s orbital with an electron in it. Now, the idea is that these half-filled orbitals are overlapping. So when I draw the second hydrogen atom, I'd like to draw it to show an area of overlap with the 1s orbital in the other hydrogen atom. And so now I can indicate the electrons, so I'll do one spin up and one spin down with the and this is the theory that these half-filled atomic orbitals will overlap to form a shared pair of electrons. And so there's a valence bond theory diagram for the hydrogen molecule to represent the single bond between the two hydrogen atoms. Okay, let's try that for HF. So I'm going to ask that you do the same idea and draw energy level diagrams, but this time for H and for F. And then draw the shape of the half-filled orbital, looking to show them to overlap. So you can try that on your own, or so pause the video, or I'll build this one with you so you can see how it works again. So the energy level diagram for hydrogen involves that 1s orbital with one electron in it, and for fluorine, we'll have 2 electrons in the 1s, 2 electrons in the 2s, and then in the 2p, we know there's a p5 ending here. And so you'll notice that the half-filled orbitals are here and here. So we're looking really at the 2pz, if you will, orbital in the fluorine atom. Okay, so for a hydrogen 1s, I'm still going to draw it in a circle like this, really representing a sphere in 3 dimensions, and label it 1s. And now for the fluorine, I need to draw a p orbital. So I'm going to show that dumbbell-shaped orbital and indicate now the electrons in the region of overlap. And so the idea is that we're representing the bond between hydrogen and fluorine. It's represented by the area of overlap of these orbitals. Okay, now I'm going to go beyond our curriculum now and show you the example of methane. So we can write an energy level diagram for carbon, and you'll be quite familiar with that. 1s2, 2s2, and 2p2. And then thinking of our energy level diagram for hydrogen, we remember that there's that electron in the 1s orbital. Okay, so if we think of the bonding in methane, carbon is making 4 single bonds to each of the hydrogens. And yet you'll notice here that we only have 2 half-filled orbitals. So it seems like carbon's only able to make 2 bonds. And here's where the theory is amended to include the concept of hybridization or hybrid orbitals. So I'm going to underline in red here 4 orbitals: the 2s orbital, the 2px, the 2py, and the 2pz. And the idea here with hybridization is that these 4 orbitals actually blend to become 4 equal energy orbitals, and we call them the 2 because n equals 2 here, but we call them sp3 orbitals. So where did I get this term sp3? Well, the superscript tells you the number of orbitals that were combined to make each of these. So the superscript on s is a 1, and you'll notice that there was 1 s orbital used here, and I used 3 of these p orbitals. So 3 p's and 1 s together make up 4 sp3 orbitals. Now n equals 2 at this level, and so that's why they're called 2 sp3 orbitals. When we draw an sp3 orbital, we're really looking at the blending of the sphere and the dumbbell shape. And so when we mesh these together, so when these come together, we end up drawing them as a double lobed, but one lobe being noticeably fatter than the other, like this. And so we call that an sp3 orbital. So that's supposed to be the blend then of the s, spherical s, and the dumbbell shaped p orbital. So when we go to draw these orbitals now, I can position carbon in the middle, and I'm only going to draw the fat lobe of the sp3 orbitals. So there's one of them, there's another, and there's another. And the idea is that we have the original 4 electrons from the carbon, so 1, 2, 3, 4. We now have those 1, 2, 3, 4 half filling each of the sp3 orbitals. And that sets up nicely the ability to overlap with 1s orbitals from each of the hydrogen atoms. And so we have 2 electrons in the overlap. And so this concept here is hybridization. Now hybridization will not be on our test. Okay, we're going above the 12U curriculum at this point, but I just wanted you to see the idea that the theory, the valence bond theory, does need to adopt a higher explanation, I suppose, where we blend s and p orbitals in order to obtain half-filled orbitals that can then overlap. And this sets up the correct bond angles. This theory corresponds to the correct bond angles that we're going to see when we do VSEPR theory. I'm going to draw a line between the hydrogen and fluorine atoms in HF, just to show you that the overlap of the orbitals occurs on this green line between the 2 nuclei. And this, when the overlap occurs on the axis between the 2 nuclei, we call that a sigma bond. And that happens for carbon and hydrogen bonds in methane also. Okay, one more example of hybridization. If we consider again the energy level diagram for carbon and recall those electrons distributed as such, when we think of C2H4, we realize that that ethene molecule has a double bond between the 2 carbons. And we notice then that it's bonded, each carbon is bonded to 3 atoms. We do see, though, that there are only 2 half-filled orbitals. And so there's hybridization required here, but this time we just need to take the s orbital and 2 of the p orbitals. And that will set up 3 equal energy orbitals, but this time they are sp2 orbitals, where it took 1 s and 2 of the p orbitals in order to form these hybrid orbitals. Then we also have the 2pz, if you will, as another orbital. And so the 4 electrons distribute here. So when we position the carbon, we need to draw both carbons. We need to draw these sp2 orbitals. So again, we show a fatter lobe, if you will, and those are about 120 degrees apart. And then we draw our hydrogens with our 1s orbitals. And I can label these as our sp2, two sp2 orbitals. And we can show the overlap here. Now all the overlap I'm showing you is essentially covering off the sigma bonds in this molecule, which I'm going to highlight or draw back in the ethene structure. So 1, 2, 3. Okay, so we see 1, 2, 3 sigma bonds for each carbon. Now, where is the double bond coming from? So in other words, this bond here. Well, remember this 2pz orbital. We can go back to our diagram here and draw in a dumbbell-shaped 2pz orbital. And this orbital is half filled. And so it's actually the overlap of these lobes above and below the axis between the nuclei, and it's that overlap that forms what we call the pi bond. And so the pi bond is the double bond. So when a double bond is formed, we have the sigma bonds and then the pi bond. So again, this goes far beyond what I'm testing you on. Hybridization is not there at all, but I thought it was helpful to expose you to this hybridization concept. If you have more questions about it, I'd be happy to do more examples in class. Okay, so the last part of this video is really review from grade 11. So I'll ask you to take note of the steps that I'm going to write here for drawing Lewis diagrams, and then be prepared to practice in class. Okay, so I've written these steps as 6 steps. So much like learning a dance routine, you get better at it the more you practice, and it doesn't look right unless you do the steps in order. That's what we need to do here. So hopefully this is a review for you from grade 11. So after you've copied these down, we'll do some examples. Okay, so with methane, we look at the periodic table, find carbon in group 14. There are 4 valence electrons. For each of those hydrogens, there are 4 of them, and they have 1 valence electron each, for a total of 8 electrons. So that's step 1. Step 2, we place the atoms on the page. Look for symmetry. There's 1 atom of carbon and 4 of hydrogen, then the 4 will likely be around the 1, but for sure, the atom with the highest combining capacity, the one that needs the most electrons to become stable, will be the central atom. And so we'll have carbon in the middle with 4 hydrogens around. Now we place single bonds between the atoms. Count by 2s as you go. 2, 4, 6, 8. Well, it turns out I've used up all 8 valence electrons just by placing those bonds, and so I don't have any remaining electrons to place as lone pairs. I can check for stability and see that each atom has a stable octet, while the hydrogens follow the exception of just being stable with 2, and the carbon has 8 electrons. And so we're finished. So we'll try Cl2. There are 2 chlorines, and each of them has 7 valence electrons, for a total then of 14 electrons. So I place the chlorine atoms on the page and start with the bond between the atoms, 2. Now I go to an outside atom and place lone pairs until this atom is stable. So 4, 6, 8. I'm keeping a running total. So the 2 in the bond, and then 4, 6, 8. That chlorine's now stable, and I need to get up to 14 electrons. So I come over to the other chlorine, 10, 12, 14. Is each atom stable? Yes. Do I have 14 electrons in the picture? Yes. Moving on. NH3. 5 valence electrons for the nitrogen from group 15. there are 3 hydrogens at 1 each for a total of 8 electrons. Nitrogen in the middle, hydrogen around, and now I place the electrons. 2, 4, 6. Okay, I go to now the outside atoms. Each hydrogen is stable, so now I'll look inside and place the remaining 2 electrons as a lone pair on the nitrogen. The nitrogen is stable with 8 electrons, and so we move on. Oxygen. There are 2 oxygen, 6 valence electrons each, so there's 12 electrons. Place the oxygen atoms on the page and fill in the bonds. 2. Now I go to one of the oxygens with lone pairs. So 4, 6, 8. Go to the other oxygen, 10, 12. And now I realize that this oxygen on the left is not stable, but I have reached the 12 electrons. So I'm at the very last step in terms of the steps that you copy down. I need to reposition a lone pair as a bonded pair to form a multiple bond, and in this way I satisfy the octet rule for the oxygen on the left. And so this is our final answer right here. Okay, a few more examples. HCN, H2S, the carbonate ion, and the bicarbonate ion. So you can be doing this yourself and checking in, or following along with me if you're still learning. So 1 electron for the hydrogen, 4 for the carbon, 5 for the nitrogen, a total of 10 electrons. Place the atoms on the page. Which atom has the greatest combining capacity? Which one needs the most electrons to become stable? If you're thinking carbon in group 14 with 4 valence electrons needing 4 to become stable, you're right, that's greater than what nitrogen needs or what hydrogen does. So the carbon will be in the middle with the nitrogen and the hydrogen on either side. 2, 4. The hydrogen's already stable, I'll look to the nitrogen. 6, 8, 10. Okay, I've put all 10 electrons in the picture, but I can clearly see the carbon only has 4 valence electrons right now, and so it's not stable. So we'll reposition a lone pair. That's still not going to make it stable, so I'll bring this one in, and that way I have 8 electrons around the carbon. Okay, moving on to H2S. There are 2 hydrogens, 1 valence electron each, and 1 sulfur with 6 each, and so 2 plus 6 will be 8 electrons. Position the sulfur in the middle, 2, 4. Now each hydrogen is already stable, 6, 8. Okay, what's the trick for the ions? You just need to remember to adjust your electron count. So we are going to add electrons when the charge is negative. So for anions, we add electrons. And if you had a cation, for example, the ammonium ion, right, for a cation, you would subtract electrons. But this really doesn't apply to this example. I'm just making that note in case you come across a positive ion. So electron count, 4 for the carbon, 6 for each of the 3 oxygens, and 2 for that -2 charge. So 4 plus 18 is 22, plus 2, 24 electrons. Carbon in the middle, oxygen around, and now I place 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So all 24 electrons are in the picture, but unfortunately carbon is not stable. So I'll need to reposition a lone pair, and in doing so I form a double bond. In doing so I form a double bond between this carbon and that oxygen. So I still have the 6 electrons there, 2 lone there. Now because it's an ion, I need to put square brackets and the charge outside. Now it's true that I could have positioned the double bond on the oxygen on the top left, or I could have also put it to the oxygen in the bottom here. So on a test, I only need you to draw one of these structures, but it's worth noting that the true structure is actually a blend of all 3 of these. And so we don't have a carbon-oxygen double bond. truly in this structure. We actually have 3 carbon-oxygen bonds that are all of the same length, and yet we don't have a way to communicate that symbol, or a symbol for that bond that's somewhere between a double and a single bond. So we draw all 3 structures, and we say that the true structure is actually a blend of all 3 of these. You only need to draw 1 structure on a test. You don't need to represent all resonance structures. Okay, so the last example is the bicarbonate ion, and the only part that's really tricky about this is the placement of that hydrogen. So if you're thinking carbon in the middle and 3 oxygens around, and then you're going to go and put a hydrogen there and start to set this up, that is never going to work. Okay, so the key is to know where to place the hydrogen. And I can show you with this carbonate ion over here that we actually have a lone pair on that oxygen grab the proton that's in the nucleus of this hydrogen in the water molecule. That's how the carbonate ion behaves with water, and we'll study this in our equilibrium unit. So actually that hydrogen needs to be placed off of one of the oxygens. And so I'll just restart this bicarbonate ion question here with an electron count: 1 for the hydrogen, 4 for the carbon, 18 for the oxygen, 1 more for the negative charge. And we end up with 24 electrons. Okay, so carbon in the middle, 3 oxygens around, and I just need to put that hydrogen off of one of the oxygens. Okay, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Square brackets, charge outside, check for stability. Is that carbon stable? It's not actually, so I'm going to need to reposition a lone pair. So I will just move up a little bit here to have a little bit more space and redraw the carbon in the middle with a double bond and singles to these other 2 oxygens. There's the hydrogen, and so that's our final structure. Okay, that's it.